Hello and welcome. Ever wondered why stars twinkle? That same atmospheric turbulence blurring starlight poses a huge challenge for astronomers using ground-based telescopes. It limits how clearly we can see distant objects. But scientists have a clever trick: adaptive optics, or AO. Imagine a telescope mirror that can change its shape hundreds of times per second. That's essentially what AO does. It uses a deformable mirror, controlled by a computer, to counteract the atmospheric blurring as it happens. The result? Much sharper images, almost like the telescope is in space. Now, for AO to work, it needs a reference point, a bright guide star near the object being studied. The system measures how the atmosphere distorts the guide star's light and applies the correction to the target object's light too. The problem is, bright, conveniently located natural guide stars are surprisingly rare. This severely limited how much of the sky astronomers could observe with this high-resolution technique. This is where laser guide stars, or LGS, come in. If nature doesn't provide a guide star, why not make one? Astronomers do exactly that by shooting a powerful laser beam up into the atmosphere. These lasers are often tuned to a specific color that excites sodium atoms naturally present in a layer about 90 kilometers up. These excited atoms glow, creating a small, bright artificial star right where the astronomers need it. Suddenly, almost the entire sky becomes accessible for sharp, AO-corrected observations. Here's how the LGS system sharpens the view. Light from this artificial star travels back down through the atmosphere, picking up the distortions. A special sensor measures these distortions incredibly fast. A computer calculates the corrections needed, telling the deformable mirror precisely how to adjust its shape to cancel out the blur. This closed-loop process cleans up the incoming light, giving incredibly clear views of the faint, distant objects astronomers want to study. There is one small nuance. While the laser guide star perfectly tracks the tone or shape of the distortion, the laser beam itself gets jostled by the atmosphere on its way up, making the artificial star seem to jitter slightly. This overall image motion, called tip tilt, is usually corrected using a nearby natural star. But since we only need to measure this simple jitter, the natural star can be much fainter, and finding one is much easier. So LGS systems still achieve near all sky coverage. Laser guide star adaptive optics has revolutionized ground-based astronomy. Telescopes can now achieve their theoretical best resolution, revealing fine details in galaxies, spotting planets around other stars, and even imaging the region around the supermassive black hole at the center of our Milky Way. The technology keeps improving too. Early lasers were complex, but now we rely on more robust, solid-state and fiber lasers. Some observatories even use multiple lasers at once to correct the view over a wider area. Safety is also built in, with systems to automatically detect aircraft. LGS AO isn't experimental anymore. It's standard equipment at major observatories like Keck, Gemini, and the Very Large Telescope. And it's absolutely essential for the next generation of giant telescopes currently being built. These extremely large telescopes will rely on advanced LGS systems to push the boundaries of discovery from right here on Earth.